Hello, and welcome to The Quiet Cosmos. Before we begin our journey tonight, take a moment to like the video and subscribe to the channel if you enjoy calm explorations of space and the universe. It really helps the channel grow and allows more people to discover these quiet journeys through astronomy. And if you feel like sharing, I'd love to know where you're watching or listening from tonight. Perhaps you're relaxing at home, winding down after a long day, or maybe you're listening from somewhere beneath a clear night sky where the stars are quietly shining above you. Wherever you are on Earth, you're sharing the same sky as billions of other observers, and many of those stars overhead may not be alone at all, because tonight we're exploring something quietly remarkable. When we look up at the night sky, it's easy to imagine each star as a solitary beacon, distant suns scattered across the darkness. For centuries that was the assumption. Our own sun appears alone after all, and so early astronomers naturally pictured other stars as isolated worlds of light. But the universe, as it often does, turned out to be more complicated and far more interesting. Many stars live double lives, not metaphorically, but literally. Across our galaxy, countless stars exist not alone, but in pairs, two suns locked together by gravity, orbiting a shared center in an endless cosmic dance. These systems are known as binary stars, and they are far more common than we once imagined. In fact, in many regions of the Milky Way, stars are more likely to be born with a partner than without one. These stellar partnerships can be quiet and graceful, with two stars circling each other peacefully for billions of years. But sometimes the relationship becomes far more dramatic. Gravity can pull material from one star to the other. Entire atmospheres can be stripped away. Massive explosions can occur when a star pushes its companion beyond the limits of stability. Some of the most powerful events in the universe, supernova explosions, neutron star collisions, even the creation of heavy elements like gold, can be traced back to the complex interactions between two stars sharing the same gravitational bond. So tonight, as we drift gently through the cosmos together, we're going to explore the double life of binary stars. We'll see how these stellar partnerships begin in vast clouds of cold gas, how gravity binds them together across unimaginable distances, how their relationship evolves over millions or billions of years, and how, in some cases, their quiet orbital dance ends in some of the most spectacular phenomena the universe can produce. Along the way, we'll encounter white dwarfs quietly stealing material from their partners, neutron stars spinning with incredible density, and black holes revealing themselves through the motion of an unseen companion. It's a story about gravity, time, and partnership on a cosmic scale. And perhaps the most remarkable part of all is this. When you look up at the night sky tonight, there's a good chance that many of the stars you see, those tiny points of light scattered across the darkness, are actually two stars, not one. From our distant vantage point on Earth, they appear as a single spark. But in reality, they're locked together in an ancient dance that has been unfolding for millions of years and will continue long after we're gone. So settle in, get comfortable, and let your thoughts drift outward into the quiet vastness of space. Tonight, we're going to explore the hidden partnerships of the stars and the extraordinary lives they live together. When we look up at the night sky, it is easy to imagine each star as a solitary traveller, a single sun shining quietly in its own corner of the galaxy. That image feels natural to us because our own sun appears to live alone, surrounded only by planets, asteroids, and distant comets. But the universe rarely follows our expectations. In reality, many stars are not solitary at all. A remarkable number of them are born with a partner. Two suns forming together from the same cloud of gas and dust, bound by gravity from the very beginning of their existence. Astronomers call these systems binary stars. Two stars orbiting a shared center of gravity, locked together in a gravitational relationship that can last for billions of years. What is perhaps most surprising is that binary stars are not rare curiosities. In many parts of the Milky Way galaxy, they are actually quite common. For certain types of stars, especially the more massive ones, astronomers now believe that forming in pairs may even be the most typical outcome. To understand why this happens, we have to travel far back in time, to the moment when stars themselves are first born. Stars begin their lives inside vast, cold regions of interstellar space known as molecular clouds. These clouds are enormous collections of gas and dust drifting quietly through galaxies. They can stretch across dozens of light years and contain enough raw material to create thousands of stars. Despite their enormous size, these clouds are extremely thin. The gas within them is mostly hydrogen, and the temperature is often only a few tens of degrees above absolute zero. Yet over time, gravity slowly begins to pull parts of these clouds inward. As gravity gathers more and more material together, dense pockets begin to form within the cloud. These pockets grow heavier and denser, eventually collapsing inward under their own weight. This process is called gravitational collapse, and it marks the beginning of star formation. For many years, astronomers assumed that this collapse would simply produce a single star at the center of each collapsing region, but the real universe is more complicated. During the 1970s, astrophysicist Richard Larson began studying how collapsing gas clouds behave under realistic conditions. His work showed that collapsing regions do not always remain smooth and uniform. Instead, they can fragment into smaller pieces. Imagine a large cloud beginning to shrink under gravity. As it contracts, small irregularities in density begin to grow. Regions that are slightly denser pull in more gas, becoming even denser still. Eventually, the collapsing cloud may split into two or more separate cores. Each of those cores can continue collapsing on its own, and when that happens, the result is not one star, but two. Larson's work helped establish the idea that fragmentation is a natural outcome of collapsing gas clouds. Rather than producing isolated stars, these clouds frequently divide into multiple gravitational centers. Each center then evolves into its own forming star. Later research expanded on this picture. Astrophysicists Christopher McKee and Eve Ostraker explored how turbulence inside molecular clouds influences star formation. Turbulence in this context does not mean violent storms like those in Earth's atmosphere. Instead, it refers to the chaotic motion of gas moving through the cloud at different speeds and directions. These turbulent motions create a constantly shifting landscape of density within the cloud. Some regions become temporarily compressed, while others expand and thin out. The result is a complex pattern of dense clumps embedded within a larger cloud. When gravity begins to act on these turbulent regions, multiple dense pockets can collapse at once. In other words, the cloud naturally produces more than one forming star. Another important ingredient in this story is angular momentum. This is a physical quantity describing how much rotational motion an object has. In simple terms, angular momentum measures how strongly something tends to spin. Even a very slowly rotating gas cloud contains angular momentum, and when that cloud begins to collapse, the rotation speeds up. The principle behind this is the conservation of angular momentum. The same reason an ice skater spins faster when pulling their arms inward. As the collapsing cloud becomes smaller, its rotation becomes faster. This increasing rotation can cause the collapsing gas to flatten into a rotating disk. Within that disk, instabilities can appear. Some regions may gather enough material to form additional gravitational centers. Once again, the collapsing region splits. Instead of a single star forming at the center, two forming stars may emerge, each pulling on the other through gravity. They begin orbiting a shared center of mass, establishing the partnership that will define their entire lives. For astronomers studying star formation, this realization was profound. Binary stars were not strange accidents. They were a natural consequence of how gravity, turbulence, and rotation interact inside molecular clouds. Research by astrophysicist Pavel Krupa helped reveal just how important this idea might be. Krupa studied the statistical distribution of stars in clusters and galaxies, focusing on something called the initial binary fraction. The initial binary fraction is simply the percentage of stars that are born with companions. If that fraction is high, then many stars begin their lives in pairs, and that changes how entire stellar populations evolve over time. Binary stars can exchange mass with one another, they can alter each other's lifetimes, they can even merge together or explode in dramatic ways. Because of this, the number of binaries present at the birth of a star cluster strongly influences the cluster's long-term behavior. Modern astronomical surveys have confirmed that binary stars are indeed extremely common. For stars similar to our Sun, roughly half appear to exist in binary or multiple systems. For very massive stars, the fraction may be even higher. So when we imagine the night sky filled with solitary suns, we are only seeing part of the story. In many cases, that single point of light may actually represent two stars locked together in orbit. From our distant vantage point, their light blends into a single sparkle. But up close, the reality is far more dynamic. Two stars circling one another across millions of kilometers of space, their gravity binding them together from the moment they formed. Their lives unfolding not in isolation, but in partnership. From their first moments inside a collapsing cloud, their destinies become intertwined. And that shared journey can lead to some of the most fascinating and dramatic phenomena anywhere in the universe. For most of human history, the stars appeared perfectly solitary. Ancient observers across many cultures studied the night sky carefully. They mapped constellations, followed the wandering motion of the planets, and tracked the slow seasonal shifts of familiar star patterns. Yet to the naked eye, nearly every star looked like a single point of light. If two stars happened to appear close together in the sky, it was usually assumed that this closeness was only an illusion. One star might simply lie much farther away than the other, aligned along the same line of sight. From Earth, they would appear side by side, even though they were separated by enormous distances. This assumption seemed perfectly reasonable. After all, without powerful telescopes, there was no obvious way to tell the difference. That began to change during the late 1700s, when telescopes improved enough for astronomers to resolve finer details in the night sky. One of the most important figures in this story was the astronomer William Herschel. Herschel is widely remembered today for discovering the planet Uranus in the year 1781. But his work extended far beyond planetary discovery. He was deeply fascinated by the structure of the heavens and spent countless nights studying stars through carefully crafted telescopes of his own design. During these observations, Herschel began noticing something intriguing. Certain stars that appeared single to the naked eye were revealed by telescopes to be pairs of stars sitting very close together. These were called double stars. At first, Herschel suspected that most of these pairs were simply chance alignments, two unrelated stars appearing close together only because they happened to lie along the same line of sight from Earth. However, Herschel was not satisfied with simple assumptions. He decided to test the idea through careful, patient observation. Over many years, he repeatedly measured the positions of several double stars relative to each other. If the stars were unrelated and merely aligned by chance, their relative positions should remain mostly unchanged over time. But that is not what Herschel saw. Instead, he noticed that in some pairs, the stars slowly shifted positions relative to one another. One star might drift slightly around the other over the course of years or decades. This subtle motion suggested something remarkable. The stars were not simply aligned by chance. They were moving around one another under the influence of gravity. In other words, they were physically connected systems. In the year 1782, Herschel formally proposed that many double stars were actually gravitationally bound pairs, two stars orbiting a shared center of mass. This was a revolutionary realization. Until then, gravity had primarily been studied within our own solar system, governing the motions of planets and moons. Herschel's observations suggested that the same laws of gravity also shaped the motion of stars themselves. The universe was not merely a scattered collection of isolated suns. It was filled with gravitational relationships. As telescopes improved and observations accumulated, other astronomers began exploring this new frontier. One important figure in the early mathematical study of binary stars was the French astronomer Félix Savary. In the year 1827, Savary performed one of the first detailed calculations of a binary star orbit. The system he studied was known as C Ursae Majoris, a pair of stars located in the constellation Ursa Major. Using careful measurements of how the two stars moved relative to one another over time, Savary applied the laws of celestial mechanics to determine the shape and size of their orbit. His calculations showed that the stars were following a path consistent with gravitational motion, much like planets orbiting the Sun. Savary's work demonstrated that the tools used to understand planetary motion could also be applied to stars themselves. The same mathematical principles that described the orbit of Earth around the Sun could describe the motion of two stars around their shared center of gravity. This connection reinforced the idea that the laws of physics were universal. The same gravitational rules applied across the entire cosmos. As the 19th century progressed, the number of known double stars continued to grow. Observers across Europe and North America began carefully cataloguing these systems. Among the most dedicated of these observers was Sherburne Wesley Burnham, an American astronomer with an extraordinary talent for patient observation. Burnham began his astronomical career in an unusual way. He was originally a court reporter by profession, not a professional scientist. Yet his passion for astronomy led him to spend countless nights studying the sky through telescopes. Working largely on his own, Burnham discovered and catalogued thousands of double star systems. His observations were so precise and so extensive that professional observatories soon recognized the importance of his work. Eventually, he was invited to join major research institutions, where he continued expanding his catalogue. Burnham's discoveries revealed something that had once seemed unlikely. Double stars were not rare at all. They appeared throughout the sky in significant numbers. His monumental catalogue, published toward the end of the 19th century, listed over 13,000 double stars. Many of these systems were later confirmed to be genuine gravitational binaries. Burnham's work helped shift the perception of binary stars from unusual curiosities to important components of the stellar population. Meanwhile, observatories began launching more systematic programs dedicated specifically to studying double stars. One of the most influential efforts emerged at the Lick Observatory in California, established in the late 19th century atop Mount Hamilton. Lick Observatory possessed some of the most advanced telescopes of its time. Astronomers there conducted one of the first organized surveys dedicated to measuring double stars with precision. The Lick Observatory Double Star Survey focused on repeatedly observing known star pairs and carefully recording their relative positions. These measurements were taken over many years, sometimes over several decades. This long-term approach was essential. Binary star orbits can take many years to complete. Some systems orbit each other in a few decades, while others require centuries or even millennia to finish a single revolution. By tracking these slow changes in position over time, astronomers could determine whether a pair of stars was truly gravitationally bound. If the stars moved in a smooth curved path around each other, that was strong evidence of orbital motion. Their behavior followed the predictions of Newton's law of universal gravitation. If their positions remained fixed relative to each other, or drifted in unrelated directions, then the pair was likely just an optical double, a chance alignment of unrelated stars. Over time, these careful measurements produced clear results. Many double stars were genuine binary systems. They were not simply neighbours in the sky. They were gravitational partners, locked in long, lasting orbits that could span hundreds of years. This realization transformed astronomy in subtle but profound ways. Binary stars provided astronomers with a powerful new tool. By measuring the motion of stars around each other, scientists could determine their masses using the laws of gravity. Mass is one of the most fundamental properties of any star. It controls how hot the star burns, how bright it shines, and how it will eventually end its life. Yet for a long time, measuring stellar mass directly was nearly impossible. Binary stars change that. When two stars orbit one another, their motion reveals the strength of the gravitational pull between them. From that motion, astronomers can calculate how massive the stars must be. In a sense, binary stars allowed gravity itself to become a measuring instrument. And so, what began as a simple curiosity, pairs of stars sitting close together in the night sky, gradually became one of the most valuable tools in astrophysics. Two stars circling one another in the darkness, quietly revealing the invisible forces that shape the universe. If you could quietly drift above the disk of the Milky Way and look down upon it from far outside, the galaxy might appear as a calm spiral of light. Hundreds of billions of stars arranged along graceful arms, glowing softly across a vast disk more than 100,000 light-years wide. From that distant perspective, it might still be tempting to imagine those stars as solitary suns. But modern astronomy has revealed something very different. Hidden within that sea of light is an enormous population of stellar partnerships. Binary stars are not just occasional curiosities scattered here and there. They are woven throughout the structure of the galaxy. In fact, for many types of stars, living with a companion appears to be entirely normal. This realization did not come from a single discovery. Instead, it emerged slowly through careful statistical studies of large numbers of stars. Astronomers began asking a simple but powerful question. Out of all the stars in our galaxy, how many actually belong to binary systems? To answer that question, researchers needed to examine thousands of stars in detail, carefully identifying companions and measuring their motions. One particularly influential study was carried out by astronomer David Rogovin and his collaborators during the early 21st century. Rogovin focused on stars that are similar to our Sun, often called solar-type stars. These stars have masses roughly comparable to the Sun and represent a very common category within the galaxy. His team examined a large sample of nearby stars within about 25 parsecs of Earth. A parsec is an astronomical unit of distance equal to a little more than 3 light-years, so 25 parsecs corresponds to a region roughly 80 light-years across. Within this relatively small neighbourhood of space, Rogovin and his colleagues conducted an extremely detailed census of stellar companions. They combined multiple detection techniques, including direct imaging, spectroscopic measurements, and long-term positional tracking. What they found was both simple and surprising. Roughly half of all Sun-like stars appear to have at least one stellar companion. Some exist as pairs, orbiting each other in binary systems. Others belong to even more complex arrangements involving 3 or more stars gravitationally bound together. In other words, if you gathered a random group of stars similar to our Sun, there would be a very good chance that many of them would not be alone. But the story becomes even more striking when we look at more massive stars. Massive stars are those several times heavier than the Sun. They burn their nuclear fuel much faster and shine with far greater luminosity. Many of them are blue or white in colour and are often found within young star clusters. Astronomer Hugues Saana has spent years studying these powerful stars, particularly those located in massive star-forming regions. His research focused on a population of hot, massive stars known as O-type stars. These are among the most luminous stars in the universe. Some can shine hundreds of thousands of times brighter than the Sun. By examining the spectra and motions of these stars, Saana and his colleagues discovered something remarkable. A very large fraction of these massive stars exist in binary systems. In some surveys, the fraction approaches 70% or even higher. That means that for these massive stars, forming with a companion is not merely common. It may actually be the dominant outcome. Why would massive stars be so likely to form in pairs? To understand that, astronomers have turned to sophisticated computer simulations of star-forming clouds. One leading researcher in this field is Matthew Bate, an astrophysicist who studies the physics of star formation through large-scale numerical simulations. Bates' work focuses on modelling what happens when a cold molecular cloud begins collapsing under gravity. These simulations attempt to capture the complex physics inside the cloud, including gravity, turbulence, gas pressure, and rotation. Because these processes interact in highly complicated ways, the calculations require enormous computational power. Modern supercomputers can simulate the collapse of large regions of gas containing many times the mass of the Sun. As the simulation evolves, dense regions begin forming within the cloud, eventually giving rise to individual protostars. One of the consistent outcomes of these simulations is fragmentation. Rather than collapsing into a single star, the cloud frequently splits into multiple dense cores. These cores form stars that begin interacting gravitationally almost immediately. Some pairs of protostars settle into stable orbits around one another. Others form temporary groupings where several young stars orbit within a small region before eventually separating or merging into pairs. What emerges from these simulations is a picture of star formation that is lively and dynamic. Young stars are born in crowded environments where gravitational interactions are common. Close encounters, exchanges of energy, and the formation of binary pairs naturally arise from the chaotic motion of gas and gravity. Binary stars are therefore not rare accidents. They are a natural consequence of how stars form. But detecting these stellar partnerships is not always easy. Some binary stars orbit each other at enormous distances, separated by hundreds or even thousands of astronomical units. An astronomical unit is the average distance between Earth and the Sun. Other binaries are so close together that their separation might be only a few million kilometers. In some cases, the stars orbit each other in just a few days. Because of this enormous range in separation and orbital period, astronomers must use many different techniques to identify binary systems. One of the most powerful new tools for discovering hidden binaries comes from a remarkable space mission, operated by the European Space Agency. This mission is called Gaia. Launched in the year 2013, the Gaia spacecraft is designed to measure the positions and motions of stars with extraordinary precision. It operates by repeatedly scanning the sky and recording the exact positions of stars relative to one another. The level of precision achieved by Gaia is astonishing. For many stars, Gaia can measure positional shifts as small as a few microarcseconds. A microarcsecond is an angle so tiny that it would correspond to the width of a human hair seen from several thousand kilometers away. By measuring stellar positions with such accuracy, Gaia can detect extremely subtle motions. When a star has an unseen companion, its motion through space may appear to wobble slightly as the two stars orbit their shared center of mass. Even if the companion star is too faint to see directly, this wobble can reveal its presence. Over time, Gaia has collected measurements for more than 1 billion stars across the Milky Way. Within that vast dataset, astronomers are identifying enormous numbers of binary systems that were previously invisible to us. Some are wide pairs separated by great distances. Others are close companions revealed only through their gravitational influence. As Gaia continues its mission, the census of binary stars within our galaxy continues to grow. What once seemed like a sky filled with isolated stars now appears far more interconnected. Hidden among the points of light are countless stellar partnerships. Some orbit slowly over centuries, others circle each other in a matter of hours. Together they form a complex population of gravitational relationships spread throughout the Milky Way. And each of those partnerships carries its own story, a shared beginning within a collapsing cloud, a long orbital dance shaped by gravity, and sometimes a dramatic ending written in the physics of stellar evolution. If two stars are quietly orbiting each other somewhere in the galaxy, there is no signpost announcing their partnership. From Earth, they often appear as nothing more than a single point of light. Even with a telescope, the vast distances between us and those stars can make their relationship difficult to see directly. Astronomers therefore rely on several different observational techniques to uncover these hidden systems. Over time, these techniques have been grouped into 4 main observational classes. Each one reveals binary stars in a different way, depending on how the two stars move and how their light reaches us. The first and perhaps most straightforward type is known as a visual binary. In a visual binary system, both stars can be directly seen through a telescope as separate points of light. The two stars appear close together in the sky, and careful observation over time reveals that they slowly move around one another. These orbital motions are usually very gradual. Some visual binary stars take decades to complete a single orbit. Others require centuries. Because of this, astronomers must observe them patiently over long periods of time. By measuring how the positions of the stars change year after year, scientists can map the shape of their orbit. One famous example is the bright star Sirius. Through a telescope, Sirius is accompanied by a much fainter companion known as Sirius B. This small, dense star is a white dwarf, and it orbits the much brighter Sirius A roughly once every 50 years. Visual binaries offer an enormous advantage. Because the two stars can be seen separately, astronomers can measure their positions directly and calculate their orbital paths with relatively high accuracy. However, not all binary systems are so conveniently spaced. In many cases, the stars are so close together that even powerful telescopes cannot separate them visually. This is where the second detection method becomes essential. Some binaries are known as spectroscopic binaries. Instead of detecting two separate points of light, astronomers examine the light coming from what appears to be a single star. When that light is passed through a spectrograph, it spreads into a spectrum, a detailed pattern of colors containing dark absorption lines. These lines are produced by specific chemical elements in the star's atmosphere, such as hydrogen, calcium, and iron. Under normal circumstances, those spectral lines appear at very precise wavelengths. But if a star is moving toward or away from Earth, the wavelengths of its spectral lines shift slightly. This phenomenon is known as the Doppler effect. The Doppler effect was first described by the Austrian physicist Christian Doppler in the year 1842. It occurs whenever a wave source moves relative to an observer. A familiar example occurs with sound. When an ambulance passes by with its siren active, the pitch of the siren changes as the vehicle approaches and then moves away. These sound waves are compressed while approaching, producing a higher pitch, and stretched while receding, producing a lower pitch. Light behaves in a similar way. When a star moves toward Earth, the wavelengths of its light become slightly shorter, shifting toward the blue end of the spectrum. When the star moves away, the wavelengths stretch toward the red end. Astronomers call this shift redshift and blue shift. In a spectroscopic binary system, Two stars orbit each other closely enough that their motion alternately carries them toward and away from Earth. As they orbit, the spectral lines in their combined light shift back and forth in a repeating pattern. By measuring this rhythmic motion in the spectrum, astronomers can detect the presence of two stars even if they cannot be visually separated. In some spectroscopic binaries, the spectral lines of both stars are visible and move in opposite directions as the stars orbit their shared center of mass. In other cases, only one set of lines appears, indicating that one star is much brighter than the other. Either way, the shifting pattern reveals that a gravitational partnership is present. Another fascinating type of binary system reveals itself through changes in brightness rather than motion. These are known as eclipsing binaries. In an eclipsing binary, the orbital plane of the stars is aligned in such a way that, from Earth's perspective, one star periodically passes in front of the other. When this happens, the total brightness of the system dips slightly. The dimming occurs in a regular pattern as the stars continue their orbit. By carefully measuring these variations in brightness, astronomers can learn an extraordinary amount about the system. The depth of each eclipse reveals how much light is being blocked. The timing of the eclipses reveals the orbital period. The shape of the brightness curve can even reveal the sizes and temperatures of the stars. In recent years, one of the most powerful tools for discovering eclipsing binaries has been the Kepler Space Telescope. Launched by the United States Space Agency NASA in the year 2009, Kepler was designed primarily to search for planets orbiting distant stars. It did this by monitoring the brightness of more than 100,000 stars simultaneously, looking for tiny dips in brightness caused by planets passing in front of their host stars. But Kepler also detected something else: thousands of binary star systems where one star regularly eclipsed the other. Because Kepler measured brightness with extraordinary precision, it revealed many eclipsing binaries that had never been noticed before. Some of these systems orbit each other in just a few days. Others complete an orbit in less than 24 hours, placing the stars extremely close together. The fourth major detection method involves a more subtle effect known as astrometric motion. In an astrometric binary system, only one star is visible through a telescope. Its companion may be too faint or too small to see directly. However, as the two stars orbit their shared center of mass, the visible star does not travel through space in a perfectly straight line. Instead, it traces a tiny wobbling path. By measuring that wobble with extreme precision, astronomers can infer the presence of the unseen companion. This technique has become especially powerful with the arrival of highly precise space observatories, including the Gaia spacecraft. Gaia measures stellar positions with extraordinary accuracy, allowing astronomers to detect minute deviations in a star's motion. These subtle shifts can reveal the gravitational influence of an invisible partner. In addition to these detection techniques, astronomers have also developed innovative optical technologies to resolve extremely close stellar pairs. One important breakthrough came from the development of optical interferometry. Astronomer Antoine Lebeyrie pioneered this technique during the 1970s. Optical interferometry works by combining light from multiple telescopes separated by some distance. By carefully analyzing how the light waves interfere with one another, astronomers can achieve the resolving power of a much larger telescope. This technique allows scientists to distinguish stars separated by extremely tiny angles in the sky. Another clever method is known as speckle interferometry, developed by physicist David Fried. Earth's atmosphere constantly distorts incoming starlight, causing stars to twinkle. While this twinkling is beautiful to the eye, it blurs fine details when astronomers attempt high-resolution observations. Speckle interferometry overcomes this problem by taking extremely short exposure images of stars. Each image captures a frozen pattern of atmospheric distortion. By combining many such images using mathematical analysis, astronomers can reconstruct a much sharper image of the star system. This method has allowed many extremely close binary stars to be resolved that would otherwise remain hidden. Together, these techniques form a remarkable toolkit for discovering binary systems. Some binaries reveal themselves through motion, others through changes in brightness. Some are detected through subtle spectral shifts, while others appear through tiny wobbles in their position across the sky. Each method uncovers a different piece of the hidden population of stellar partnerships scattered across the Milky Way. And as our instruments grow more precise, the universe continues to reveal just how many stars are living their lives not alone, but together. When two stars form together, bound by gravity, their motion is not simply a matter of one star circling the other like a planet around the Sun. The reality is more subtle and in some ways more elegant. Both stars move. Each one responds to the gravitational pull of the other, and together they orbit a point in space known as the barycenter. The barycenter is the shared center of mass of the system. It is the balance point where the gravitational influence of the two stars is perfectly balanced. You can imagine something similar with a playground seesaw. If two children of equal weight sit on opposite ends, the pivot point lies exactly in the middle. But if one child is heavier than the other, the balance point shifts closer to the heavier side. Binary stars behave in exactly the same way. If the two stars have identical mass, the barycenter lies halfway between them. Each star traces a circular or elliptical orbit around that central point. Their motion is symmetrical, like two dancers moving around an invisible marker on the floor. But if one star is heavier than the other, the barycenter moves closer to the more massive star. In extreme cases, the barycenter may even lie inside the larger star itself. When this happens, the heavier star appears to wobble slightly while the smaller star travels in a wider orbit. This shared orbital motion is governed by the same physical laws that control the motion of planets within our solar system. The first major insight into orbital motion came from the work of Johannes Kepler in the early 17th century. Kepler studied the precise observations of planetary motion recorded by the Danish astronomer Tycho Brahe, and used them to uncover three mathematical laws describing how planets move around the Sun. Kepler's first law states that planets travel along elliptical paths rather than perfect circles. An ellipse is a stretched circle with two focal points. In the case of planetary orbits, the Sun occupies one of those focal points. Kepler's second law describes how the speed of an orbiting object changes as it moves along its path. When a planet approaches the Sun, it speeds up. When it moves farther away, it slows down. Kepler's third law reveals a deeper relationship between the size of an orbit and the time required to complete it. In simplified form, it states that the square of the orbital period is proportional to the cube of the orbital distance. Much later, Isaac Newton provided the physical explanation behind Kepler's observations. Newton's law of universal gravitation revealed that every object with mass attracts every other object with mass. The strength of this gravitational attraction depends on two factors: the masses of the objects involved and the distance between them. Newton expressed this relationship in a mathematical equation that became one of the most famous formulas in science. It can be written in words as: the gravitational force equals the universal gravitational constant multiplied by the mass of the first object multiplied by the mass of the second object, divided by the square of the distance between their centers. This simple relationship explains why planets remain in orbit around the Sun, and why moons orbit their planets. It also explains the motion of binary stars. When two stars orbit each other, their motion follows the same gravitational principles. The size of the orbit and the time required to complete one revolution depend on the masses of the stars and the distance between them. This leads to a remarkable possibility. By observing how two stars move around each other, astronomers can calculate their masses. Mass is one of the most fundamental properties of a star. It determines how much pressure builds inside the star's core, how hot the core becomes, how quickly nuclear fusion proceeds, and ultimately how long the star will live. Yet measuring stellar mass directly is extremely difficult. Stars are incredibly distant, and we cannot place them on scales or measure them physically. Binary stars provide the solution. By carefully measuring the orbital period of a binary system and the size of its orbit, astronomers can apply the laws of gravitation to determine the combined mass of the system. If the motion of each star can be measured individually, it becomes possible to calculate the mass of each star separately. In this way, binary stars act as natural laboratories for testing the laws of gravity and measuring the fundamental properties of stars. But gravity can become far more complicated when more than two bodies are involved. The mathematical challenge of predicting the motion of three gravitationally interacting objects is known as the three-body problem. This problem fascinated mathematicians and physicists for centuries. In the late 19th century, the French mathematician Henri Poincaré made groundbreaking contributions to its study. Poincaré discovered that the motion of three gravitational bodies can behave in surprisingly complex ways. Unlike the predictable elliptical paths of two-body systems, three-body interactions can produce chaotic behavior. Small differences in initial conditions can lead to dramatically different outcomes over time. A 3-star system might remain stable for millions of years, with the stars orbiting in a hierarchical arrangement. In other cases, close gravitational encounters may fling one star outward, while the remaining two form a tighter binary pair. Poincaré's work revealed that gravitational systems could exhibit chaos, meaning that long-term predictions become extremely difficult. This insight had profound consequences for celestial mechanics, and eventually helped inspire the modern, mathematical field known as chaos theory. Despite these complexities, binary stars themselves remain comparatively well behaved. With only two bodies interacting gravitationally, their motion can be described with remarkable precision. Astronomers take advantage of this stability. By tracking the orbital motion of binary stars over time, researchers can test the predictions of gravitational theory under real cosmic conditions. Observations of binary stars have helped confirm Newtonian gravity, and later provided tests of Einstein's theory of general relativity. For example, certain binary systems containing neutron stars exhibit extremely precise orbital motion. In some cases, astronomers have observed subtle changes in those orbits caused by the emission of gravitational waves, a prediction made by Einstein's theory. In this way, binary stars become more than just interesting stellar relationships. They serve as natural laboratories for physics itself. Even today, with powerful telescopes and sophisticated models of stellar interiors, measuring stellar mass remains one of the most important challenges in astrophysics. Binary stars remain the most reliable method for doing so. Whenever astronomers discover a new binary system, especially one where the orbital motion can be measured precisely, they gain an opportunity to determine the masses of the stars involved. Those measurements help refine models of stellar evolution, improve our understanding of nuclear fusion inside stars, and reveal how different types of stars live and die. So while the night sky may appear peaceful and still, hidden within it are countless pairs of stars tracing graceful paths around invisible balance points, each pair quietly following the geometry of gravity, each orbit revealing a little more about the fundamental laws that shape the universe. When two stars orbit each other at great distances, their relationship can remain quiet and uncomplicated for billions of years. Each star shines, burns its nuclear fuel, and traces a graceful path around the shared center of gravity with little disturbance. But when stars orbit closer together, the situation changes dramatically. Gravity does not simply hold the pair in orbit, it begins to reshape them. This reshaping occurs through a process known as tidal interaction. The idea is similar to something that happens much closer to home here on Earth. Our planet experiences tides because the Moon's gravity pulls slightly more strongly on the near side of Earth than on the far side. This difference in gravitational pull stretches Earth very slightly, raising ocean tides on opposite sides of the planet. Although Earth appears solid, even rock can flex a tiny amount under gravitational stress. Stars are far more flexible. A star is not a solid object at all. It is an enormous sphere of hot plasma made mostly of hydrogen and helium gas heated to temperatures of millions of degrees. Inside a star, matter behaves like a flowing fluid. Gas rises, sinks, circulates and moves under the influence of gravity, pressure and magnetic fields. Because of this fluid nature, stars respond strongly to the gravitational pull of nearby companions. In a close binary system, each star pulls unevenly on the other. The side of the star facing its companion experiences a slightly stronger gravitational force than the side facing away. This difference stretches the star along the line connecting the two objects, producing what astronomers call tidal bulges. Instead of remaining perfectly spherical, the star becomes slightly elongated, rather like a soft water balloon gently squeezed from opposite sides. These distortions are usually small compared with the enormous size of the star. A typical star might have a diameter of several million kilometers, while the tidal stretching might change that shape by only a small fraction of a percent. Yet even small distortions can have profound consequences over long periods of time. One of the most important effects involves the rotation of the stars. Many stars rotate independently, spinning slowly around their own axes. Our own Sun, for example, rotates roughly once every 25 days near its equator. But in close binary systems, tidal forces gradually alter this rotation. As the stars orbit each other, the tidal bulges raised on their surfaces do not always point exactly toward the companion star. Internal friction within the stellar plasma causes the bulges to lag slightly behind the line connecting the two stars. This misalignment creates a subtle but continuous torque, a twisting force that slowly transfers angular momentum between rotation and orbital motion. Over time, this process changes the spin of the stars. The French astrophysicist Jean-Paul Zahn carried out some of the most influential theoretical work describing this phenomenon. Zahn developed detailed mathematical models explaining how tidal forces dissipate energy inside stars. His research focused on a process called tidal friction. Inside a star, the gas is constantly moving through complex patterns of convection and circulation. As tidal distortions push and pull on this moving plasma, energy is gradually converted into heat through internal friction. This energy loss alters the rotation of the star. Given enough time, tidal friction can cause a remarkable outcome known as tidal synchronization. In a tidally synchronized system, a star's rotation period becomes exactly equal to its orbital period. The same side of the star always faces its companion. A familiar example of this phenomenon exists much closer to Earth. Our moon is tidally locked to our planet. It rotates once on its axis in exactly the same time that it takes to orbit Earth. As a result, the same hemisphere of the moon always faces us. Close binary stars can reach a similar state. If two stars orbit each other every few days, tidal forces may eventually slow or accelerate their rotation until each star spins at precisely the same rate as the orbital motion. The result is a stable configuration in which each star continually presents the same face toward the other. This process can take millions or sometimes hundreds of millions of years, depending on how close the stars are and how efficiently tidal energy dissipates within them. But once tidal synchronization occurs, the system enters a new phase of stability. However, tidal interactions involve more than just gravity and fluid motion. Stars also possess magnetic fields. These magnetic fields are generated by the movement of electrically charged plasma within the stellar interior. The study of this interplay between magnetic fields and fluid motion is known as magnetohydrodynamics. One of the pioneers of this field was the Swedish physicist Hannes Alfvén. During the mid-20th century, Alfvén developed many of the fundamental concepts describing how magnetic fields behave within conducting fluids such as plasma. His work helped scientists understand phenomena ranging from solar flares to the behavior of plasma in interstellar space. In binary star systems, magnetic fields can interact with tidal forces in complex ways. As the stars rotate and orbit each other, their magnetic fields may connect or twist together through surrounding plasma. This interaction can produce streams of charged particles flowing between the stars. Magnetic braking can also occur. In this process, stellar winds carrying magnetized plasma flow outward from the stars. These winds carry away angular momentum, gradually slowing the rotation of the stars and altering the orbital dynamics of the system. Over long periods of time, the combined effects of tidal friction, magnetic fields, and gravitational interaction can significantly reshape the evolution of binary stars. Some systems settle into stable synchronized orbits, where both stars rotate in perfect harmony with their orbital motion. Others continue evolving, with tidal forces gradually drawing the stars closer together or transferring angular momentum from rotation into the orbit. The outcome depends on many factors: the masses of the stars, their separation, their internal structure, and the strength of their magnetic fields all influence the final result. What makes this process particularly fascinating is that it reveals just how dynamic stars truly are. From a distance, a star may appear as a steady, unchanging point of light, yet within binary systems, stars are constantly responding to the gravitational presence of their partners. Their shapes shift slightly under tidal forces, their rotations adjust through internal friction, their magnetic fields twist and interact through surrounding plasma. Over millions of years, these subtle effects accumulate, quietly reshaping the relationship between the two stars. What began as a simple orbital partnership gradually becomes a complex physical interaction. Gravity pulls them together, tides stretch their surfaces, magnetic forces weave invisible connections through the surrounding plasma. In the stillness of space, the stars continue their long dance, and with every orbit, the forces between them gently reshape the future of the system. When two stars orbit one another, gravity does more than simply hold them together. It also defines invisible territories around each star, regions where its gravitational pull dominates the motion of nearby gas and plasma. These regions form a kind of gravitational landscape, an invisible map of forces stretching through the space between the two stars. Within this landscape, matter follows paths determined not just by one star, but by the combined gravity of both. Understanding this hidden structure became possible through the work of the 19th century French astronomer Édouard Roche. Roche studied how gravity behaves in systems where two large bodies orbit each other. His calculations revealed that each star in a binary system possesses a surrounding region where its gravitational influence is strongest. Within this region, gas and plasma remain gravitationally bound to that particular star. Astronomers now call this region the Roche lobe. You can imagine each star enclosed within a kind of invisible bubble. Inside that bubble, material naturally falls toward the star at its center. Outside the bubble, the gravitational pull of the companion star becomes stronger. These Roche lobes are not perfect spheres. Instead, they form a slightly distorted teardrop-shaped structure, stretched along the line connecting the two stars. The exact shape depends on the masses of the stars and the distance separating them. In a binary system where both stars have similar masses, the Roche lobes are roughly equal in size. In systems where one star is much heavier, the larger star claims a greater share of gravitational territory. But the most fascinating feature of this gravitational landscape lies at the narrow point where the two Roche lobes nearly touch. At this location, the gravitational pull of both stars becomes delicately balanced. Gas at this point can move from one star to the other with relatively little resistance. This critical region is closely related to a set of special locations in gravitational systems known as Lagrange points. The concept of Lagrange points was developed by the mathematician Joseph Louis Lagrange during the 18th century. While studying the motion of celestial bodies under gravity, Lagrange discovered that in a system containing two large masses, there exist several points where the gravitational forces and orbital motion balance perfectly. At these points, a small object can remain in a relatively stable position relative to the two larger bodies. In a binary star system, 5 such Lagrange points exist. Astronomers label them using the names Lagrange 1 through Lagrange 5. The most important for binary star evolution is Lagrange point 1. This point lies directly between the two stars, along the line connecting their centers. At this location, the gravitational pull from each star and the centrifugal forces of orbital motion combine in such a way that material can move between the stars with remarkable ease. Lagrange point 1 essentially forms a narrow gravitational bridge. If gas from one star reaches this region, it can begin flowing toward the other star. Under ordinary circumstances, the outer layers of a star remain safely contained within its Roche lobe. Gravity holds the star's atmosphere in place, preventing large amounts of gas from escaping. However, stars do not remain static throughout their lives. As stars evolve, their internal structure changes. Many stars expand dramatically as they exhaust hydrogen fuel in their cores and begin burning heavier elements. During these later stages of evolution, a star may grow many times larger than it was during its youth. Our own Sun, for example, is expected to expand into a red giant several billion years from now. At that stage, its outer atmosphere will extend far beyond the orbit of Mercury and possibly even reach the current orbit of Earth. In a binary system, such expansion can have dramatic consequences. If a star grows large enough to fill its Roche lobe, its outer layers reach the boundary where its gravitational control begins to weaken. At that point, the star can no longer hold all of its gas within its own gravitational territory. Material begins to spill outward through the region near Lagrange point 1. This process is known as Roche lobe overflow. Once it begins, gas from the expanding star can flow steadily toward its companion. Instead of drifting away into space, the escaping material is captured by the gravitational pull of the second star. The transfer of matter between stars marks the beginning of a far more intimate relationship. Gas streaming through the gravitational bridge does not simply fall directly onto the companion star. Because both stars are orbiting each other, the gas usually forms a rotating stream that spirals inward. In many cases, this stream spreads into a rotating disk of material surrounding the receiving star. Astronomers call this structure an accretion disk. Within the disk, gas gradually loses energy and spirals inward, eventually settling onto the surface of the star. The process can release enormous amounts of energy. As gas accelerates and compresses within the disk, it heats up dramatically, often reaching temperatures of hundreds of thousands, or even millions of degrees. Some of the most energetic phenomena in the universe arise from this kind of mass transfer. But even before dramatic events occur, the geometry of the Roche lobes already determines the future path of the binary system. If the two stars remain well inside their Roche lobes, their interaction remains limited to gravitational tides and magnetic effects. Their evolution may proceed relatively independently. However, once one star fills its Roche lobe, the system enters a new phase. Mass begins moving from one star to the other. Angular momentum is redistributed throughout the system. The orbit itself may gradually change in response to these transfers of matter and energy. In some cases, the receiving star grows heavier and brighter as it accumulates material from its partner. In other situations, the mass transfer becomes unstable. The donor star may lose its outer layers rapidly, dramatically altering its structure. All of this behavior emerges from the simple geometry defined by the Roche lobes and the delicate balance of forces at Lagrange point 1. What appears to be empty space between the stars is actually structured by gravity into a complex landscape of potential energy. Gas follows invisible contours defined by the gravitational field. Matter flows along pathways determined by the combined pull of both stars. The result is a dynamic and evolving relationship that can last for millions or even billions of years. Two stars orbiting quietly around a shared center of mass. Yet between them lies an invisible boundary shaped by gravity that determines whether their lives remain separate or become deeply intertwined. When that boundary is crossed, the quiet dance of binary stars transforms into something far more dramatic. When gas begins flowing from one star toward another in a binary system, it does not usually plunge directly onto the surface of the receiving star. The reason lies in one of the most important principles in physics, the conservation of angular momentum. Angular momentum describes the tendency of a rotating system to continue rotating. Once matter begins moving in a circular or orbital path, it resists falling straight inward unless something removes that rotational motion. In a binary system undergoing mass transfer, the gas leaving the donor star already carries orbital motion. As the two stars revolve around their shared center of gravity, any material escaping from one star inherits part of that motion. When this gas approaches the companion star, it cannot simply fall directly downward like rain onto a roof. Instead, it swings past the star and begins orbiting it. The result is the formation of a rotating structure known as an accretion disk. An accretion disk is a flattened disk of gas and plasma that circles around a central object. In the case of interacting binary stars, the central object may be a normal star, a white dwarf, a neutron star, or even a black hole. Within the disk, matter follows nearly circular orbits. Gas closer to the central object moves faster than gas located farther away. This difference in orbital speed creates shear between neighboring layers of the disk. You can imagine the disk as a series of rings. The inner rings rotate quickly, while the outer rings move more slowly. Because the gas is not perfectly smooth, friction develops between these layers. This friction causes the gas to gradually lose energy and spiral inward toward the central object. As the gas moves inward, gravitational energy is released. Every object falling deeper into a gravitational field loses gravitational potential energy. That lost energy must go somewhere, and in an accretion disk it is converted primarily into heat. The gas becomes extremely hot. Temperatures within accretion disks can reach tens of thousands or even millions of degrees depending on the type of central object involved. At these temperatures, the gas emits intense radiation across a wide range of wavelengths, including visible light, ultraviolet radiation, and sometimes powerful X-rays. Because of this heating, accretion disks can shine with extraordinary brightness. In some systems, the disk itself becomes brighter than the star that originally produced the gas. Understanding how these disks behave became a major challenge for astrophysicists during the 20th century. One of the most influential theoretical frameworks was developed during the 1970s by two Russian astrophysicists, Nikolai Shakura and Rashid Sunyaev. Their work introduced what is now known as the Shakura-Sunyaev accretion disk model. Shakura and Sunyaev recognized that the key problem in accretion physics is explaining how gas within the disk loses angular momentum. In order for matter to spiral inward, it must somehow transfer its rotational motion outward through the disk. The exact mechanism responsible for this transfer was not immediately obvious. To describe the process mathematically, Shakura and Sunyaev introduced a parameter representing the efficiency of internal friction within the disk, This parameter, commonly called the alpha parameter, allowed astronomers to model how turbulence inside the disk transports angular momentum outward. Their model successfully described many observable features of accretion disks, including temperature distribution, luminosity, and disk thickness. For many years, however, one crucial question remained. What actually creates the turbulence inside the disk? The answer emerged several decades later through the work of astrophysicists Stephen Balbus and John Hawley. Balbus and Hawley studied how magnetic fields interact with rotating disks of ionized gas. Their research led to the discovery of a powerful instability known as magnetorotational instability. Magnetorotational instability arises when a weak magnetic field threads through a rotating disk of plasma. Because the plasma conducts electricity, the gas becomes coupled to the magnetic field lines. If two neighboring regions of the disk are connected by a magnetic field line, their differing orbital speeds create tension along that line. The faster inner region pulls ahead, stretching the magnetic connection. This stretching acts like a spring under tension. The inner gas slows down slightly, losing angular momentum, while the outer gas gains angular momentum and moves outward. As this process repeats throughout the disk, it generates turbulence and efficiently transports angular momentum outward. This mechanism provides the missing explanation for why accretion disks behave as they do. Magnetorotational instability allows gas to gradually spiral inward, while angular momentum flows outward through the disk. The result is a steady inward drift of material toward the central object. As the gas spirals inward, its orbital speed increases dramatically. Near the center of the disk, the gas may move at thousands of kilometers per second. At these speeds, collisions between particles generate enormous amounts of heat. The gas becomes so hot that it glows intensely. This conversion of gravitational energy into radiation makes accretion disks some of the most luminous objects in the universe. In binary star systems, where a white dwarf or neutron star is accreting matter, the disk can emit strong ultraviolet radiation and X-rays. In systems involving black holes, the energies become even more extreme. Gas approaching a black hole must accelerate to incredible speeds as it approaches the event horizon. Temperatures in the inner regions of the disk can exceed many millions of degrees. These disks become powerful sources of high-energy radiation that astronomers detect across vast distances. Yet the physics of accretion disks is not limited to exotic systems involving collapsed stars or black holes. The same physical processes appear in many other cosmic environments. Young stars forming within molecular clouds are often surrounded by disks of gas and dust known as protoplanetary disks. These disks eventually give rise to planetary systems. Within them, gas slowly spirals inward toward the forming star while dust grains collide and accumulate into larger bodies. Over millions of years, those grains can grow into planetesimals, asteroids, and eventually full-sized planets. In this sense, the same accretion physics that powers some of the most energetic systems in the universe also plays a role in building planetary systems like our own. Accretion disks therefore represent a common structure throughout the cosmos. They appear around forming stars, around white dwarfs drawing gas from companions, around neutron stars producing powerful X-ray emissions, and around black holes consuming matter from their surroundings. All of these systems share the same underlying principles: gas orbiting a central object, angular momentum gradually transferred outward through turbulence, gravitational energy converted into heat and radiation as matter spirals inward. In the quiet darkness of space, these rotating disks become engines of transformation. Gas flows inward, energy flows outward, and the gentle exchange of matter between two stars can light up the universe in unexpected ways. In some binary star systems, the quiet exchange of matter between two stars becomes far more dramatic. Instead of a gentle flow of gas forming a stable disk, the transfer of material can lead to powerful bursts of light that briefly outshine the entire system. Astronomers call these systems cataclysmic variables. The name may sound rather dramatic, but it captures the essential behavior of these stars. They appear calm most of the time, shining steadily in the darkness. Then, without warning, their brightness suddenly increases by many times over before gradually fading again. To understand what drives these outbursts, we need to look at the type of stars involved. Cataclysmic variable systems contain two very different stars orbiting closely together. One of them is usually a white dwarf. The other is typically a more ordinary star, often a small cool star similar to the Sun but somewhat less massive. A white dwarf is the dense remnant left behind after a sun-like star reaches the end of its life. When a star of moderate mass exhausts its nuclear fuel, it sheds its outer layers and leaves behind a compact core. This core is incredibly dense. A typical white dwarf contains roughly the same mass as the Sun, but compressed into a sphere only about the size of Earth. A teaspoon of white dwarf material would weigh several tons under Earth gravity. The intense gravity of the white dwarf plays a crucial role in the behavior of cataclysmic variables. Because the stars in these systems orbit very close to each other, the ordinary companion star may expand until its outer layers reach the boundary of its Roche lobe. Once that happens, gas from the companion begins flowing through the gravitational bridge near Lagrange point 1. This gas forms an accretion disk around the white dwarf. The disk glows as gravitational energy is converted into heat. But the most dramatic events occur when gas finally reaches the surface of the white dwarf itself. Unlike a normal star, a white dwarf no longer generates energy through nuclear fusion in its core. It is essentially a dense ember slowly cooling over billions of years. However, when hydrogen-rich gas from the companion star accumulates on the white dwarf's surface, something extraordinary can occur. The gas forms a thin layer under enormous pressure. Because the white dwarf's gravity is so strong, the gas becomes compressed to extreme densities. Temperatures begin to rise as more material piles on top of the growing layer. Eventually, the temperature at the base of the accumulated gas becomes high enough for hydrogen fusion to ignite. But this ignition behaves very differently from the steady fusion inside an ordinary star. In a normal star like the Sun, fusion reactions occur in a stable environment, where gas pressure and temperature can adjust to regulate the reaction rate. On a white dwarf, the situation is quite different. The gas at the base of the accreted layer is supported not by ordinary gas pressure but by electron degeneracy pressure, a quantum mechanical effect that resists further compression. This unusual state of matter does not respond to heating in the usual way. When the temperature rises, the pressure does not increase enough to expand the gas and cool it down. As a result, the nuclear reactions accelerate rapidly. Hydrogen fusion begins in a runaway process known as a thermonuclear runaway. Within a very short time, the accumulated hydrogen layer undergoes an explosive burst of fusion reactions. The energy released is enormous. The outer layers of gas are blasted outward into space at speeds of hundreds or even thousands of kilometers per second. From Earth, this explosion appears as a sudden increase in brightness known as a nova. The word nova comes from a Latin term meaning new star. Early astronomers used this name because these outbursts seemed to create a new star in the sky, where none had been visible before. In reality, the star was always there. The eruption simply made it dramatically brighter for a short time. Some novae can increase their brightness by a factor of 10,000 or more within just a few days. Despite the violence of the explosion, the white dwarf itself survives. The blast ejects the accumulated gas layer into space, leaving the dense core largely intact. After the eruption, the system gradually returns to its quiet state. Meanwhile, the companion star continues losing material through the Roche lobe overflow. Gas once again begins flowing toward the white dwarf. The accretion disk reforms, and the slow accumulation of hydrogen on the white dwarf's surface begins anew. Given enough time, the conditions for another thermonuclear runaway will develop. This repeating cycle of accumulation and explosion is what defines cataclysmic variable systems. Some of these systems produce nova outbursts every few decades. Others may take hundreds or thousands of years between eruptions. Astronomers study these systems closely because they provide insight into extreme physical processes involving dense matter, nuclear fusion, and accretion physics. One of the most prominent researchers in this field has been the astrophysicist Brian Warner. Warner devoted much of his career to studying cataclysmic variable stars and their complex behavior. His work helped classify different types of cataclysmic variables and explain the mechanisms behind their brightness variations. Some systems show frequent small outbursts caused by instabilities within the accretion disk itself. Others produce the far more dramatic nova explosions triggered by thermonuclear runaways. Observing these events requires patience and coordination. Nova eruptions are unpredictable. They can occur suddenly and may last only a short time before fading again. Because of this, professional astronomers often rely on a global network of observers to monitor variable stars continuously. One important organization involved in this effort is the American Association of Variable Star Observers. This group, often called the AAVSO, coordinates observations from both professional and amateur astronomers around the world. Thousands of observers regularly monitor variable stars, recording their brightness and reporting changes. When a nova eruption occurs, these observations provide valuable data about how the system evolves during and after the explosion. This collaboration between amateur skywatchers and professional scientists has contributed to our understanding of many cataclysmic variable systems. Through careful observation, astronomers have discovered that some of these systems repeat their outburst with remarkable regularity. Each eruption begins with a slow accumulation of hydrogen-rich gas. The white dwarf quietly gathers material from its companion star layer by layer. The pressure and temperature gradually rise. Eventually, the threshold for nuclear ignition is crossed. Then, in a sudden burst of energy, the accumulated gas explodes outward into space, briefly transforming the quiet binary system into a brilliant beacon visible across vast distances. And after the eruption fades, the cycle begins again. Two stars orbiting one another, one steadily feeding the other, and every so often the balance tips just enough to ignite a sudden flash of cosmic fire. At the end of a star's life, gravity always tries to win. Throughout most of a star's lifetime, the inward pull of gravity is balanced by the outward pressure created by nuclear fusion in the core. Hydrogen atoms fuse into helium, releasing energy that pushes outward and prevents the star from collapsing. But eventually that fusion slows and stops. For stars with masses roughly similar to the Sun, the final stage of evolution leaves behind a compact stellar remnant known as a white dwarf. A white dwarf is not a star in the usual sense. It no longer produces energy through nuclear fusion. Instead, it is the exposed core of a once larger star, left behind after the outer layers have drifted away into space as a glowing planetary nebula. Despite its quiet appearance, a white dwarf is one of the most extraordinary objects in the universe. Imagine compressing the mass of the Sun into a sphere roughly the size of Earth. The result would have a diameter of only about 12,000 kilometers, yet it would still contain a mass comparable to the Sun's entire mass. The average density of such an object becomes almost unimaginable. A cubic centimeter of white dwarf material would weigh roughly a ton under Earth gravity. A spoonful would weigh as much as a large truck. What prevents such an object from collapsing even further under its own gravity? The answer lies in one of the strangest principles of quantum physics. Inside a white dwarf, matter is packed so tightly that electrons cannot move freely in the usual way. Instead, they obey a rule known as the Pauli exclusion principle. This principle states that two electrons cannot occupy the same quantum state at the same time. When electrons are squeezed extremely close together, this rule creates a powerful resistance to further compression. As gravity attempts to push matter inward, the electrons push back through a form of pressure known as electron degeneracy pressure. This pressure does not depend on temperature in the way ordinary gas pressure does. Even if the white dwarf cools down, the electrons continue resisting compression purely because of quantum mechanics. Electron degeneracy pressure becomes strong enough to halt the collapse of the star. This idea was first developed during the 1920s by the physicist Ralph Fowler. Fowler applied the newly emerging principles of quantum statistics to the problem of dense stellar remnants. Using a theory known as Fermi-Dirac statistics, he showed that electrons packed together at extremely high densities create a pressure that can support a star against gravity, even in the absence of nuclear fusion. Fowler's work marked one of the earliest applications of quantum mechanics to astrophysics. It revealed that the fate of stars could depend not only on classical physics, but also on the strange rules governing particles at the smallest scales. Yet Fowler's theory raised another important question. How much mass could electron degeneracy pressure support? If a white dwarf became heavier and heavier, gravity would grow stronger. At some point, the inward pull of gravity might overwhelm the pressure generated by degenerate electrons. Determining that critical mass became one of the most important problems in stellar physics. The answer came from the work of a young Indian physicist named Subrahmanyan Chandrasekhar. During the early 1930s, Chandrasekhar was studying the structure of white dwarf stars while travelling by ship from India to England. Using a combination of relativity and quantum mechanics, he calculated how electron degeneracy pressure behaves at extremely high densities. His calculations revealed a striking result. There exists a maximum mass beyond which a white dwarf cannot remain stable. If the mass of a white dwarf exceeds this limit, electron degeneracy pressure is no longer strong enough to support the star against gravity. The star must collapse into an even denser state. This critical mass is now known as the Chandrasekhar limit. Its value is approximately 1.4 times the mass of the Sun. Below this limit, a white dwarf can remain stable indefinitely, slowly cooling over billions of years. Above this limit, the star becomes unstable and must collapse into a more compact object. Chandrasekhar's result was initially controversial. Some prominent astronomers, including Arthur Eddington, resisted the idea that stars could collapse into such extreme states. But over time, observations and theoretical work confirmed that Chandrasekhar's calculations were correct. Today, the Chandrasekhar limit stands as one of the most important concepts in stellar astrophysics. Around the same period, the Soviet physicist Lev Landau also explored the properties of extremely dense stellar matter. Landau proposed that under sufficient pressure, electrons and protons could combine to form neutrons, creating a new state of matter far denser than a white dwarf. This idea helped to lay the groundwork for the later discovery of neutron stars. Together, the work of Fowler, Chandrasekhar, and Landau revealed that stellar remnants exist along a sequence of increasing density. White dwarfs represent the first stage, supported by electron degeneracy pressure. If a remnant becomes more massive, gravity can overcome this pressure and force the matter into even denser forms. In isolated stars, white dwarfs typically remain well below the Chandrasekhar limit. However, binary star systems introduce a complication. If a white dwarf has a companion star close enough to transfer matter through Roche-Loeb overflow, the white dwarf can slowly gain mass. Gas from the companion star accumulates on its surface through the accretion process. At first, this added mass may simply trigger nova explosions as hydrogen layers ignite and are expelled. But if the white dwarf continues gaining mass over long periods of time, its total mass gradually increases. Eventually it may approach the Chandrasekhar limit. At that point, the internal structure of the white dwarf becomes increasingly unstable. The immense pressure at its center forces atomic nuclei closer and closer together. When the mass crosses the critical threshold, the delicate balance between gravity and electron degeneracy pressure can no longer be maintained. The consequences of this instability can be extraordinary. In some cases, the entire white dwarf undergoes a catastrophic thermonuclear explosion, known as a Type Ia supernova. In other situations, the star may collapse further into an even denser object. All of these possibilities begin with the same underlying physics: a dense stellar remnant supported by quantum mechanical pressure, a companion star quietly feeding it additional mass, and gravity waiting patiently, ready to take control once the balance is finally broken. When a white dwarf quietly gathers material from a nearby companion star, the process can continue for thousands or even millions of years without attracting much attention. Gas flows inward, settles onto the surface, and gradually increases the mass of the dense stellar core. For a long time, the system may appear relatively calm, but the stability of a white dwarf depends on a very precise balance between gravity and quantum mechanical pressure. As long as the star remains below the Chandrasekhar limit, electron degeneracy pressure can support the star against collapse. However, if enough mass accumulates, that balance begins to fail. The Chandrasekhar limit lies at roughly 1.4 times the mass of the Sun. Once a white dwarf approaches this threshold, the density and temperature within its interior rise dramatically. At these extreme conditions, the carbon and oxygen nuclei inside the star begin to fuse. Unlike the stable fusion occurring in ordinary stars, this ignition takes place within matter supported by electron degeneracy pressure. Because degeneracy pressure does not respond to temperature changes in the same way as ordinary gas pressure, the star cannot expand to cool itself. Instead, the fusion reactions accelerate uncontrollably. The result is a thermonuclear runaway that spreads rapidly through the entire star. Within just a few seconds, nuclear burning races through the white dwarf's interior. Carbon and oxygen fuse into heavier elements such as nickel and iron, releasing an immense amount of energy. The energy is so great that it completely unbinds the star. The white dwarf is destroyed in a tremendous explosion known as a Type Ia supernova. Unlike the nova eruptions that occur repeatedly in some binary systems, this event is final. The star does not survive. Its entire mass is blasted outward into space at velocities of thousands of kilometers per second. For a short time, the explosion becomes extraordinarily bright. A single Type 1, a supernova, can shine with the luminosity of several billion suns combined. In distant galaxies, the explosion may briefly rival the brightness of the entire galaxy in which it occurs. Astronomers quickly realized that these explosions had another remarkable property. Because the mass of the exploding white dwarf is always close to the Chandrasekhar limit, the energy released in these explosions tends to be similar from one event to another. That means Type 1a supernovae have roughly the same intrinsic brightness. In astronomy, objects with known intrinsic brightness are extremely valuable. If scientists know how bright an object truly is, they can determine how far away it must be by measuring how faint it appears from Earth. The idea works much like observing a distant street lamp at night. If you know how bright the lamp is in reality, you can estimate how far away it must be based on how dim it appears from where you're standing. Astronomers call such objects standard candles. Type 1. A supernovae turned out to be among the most useful standard candles in the universe. Because they are incredibly luminous, they can be observed across enormous cosmic distances. Light from these explosions can travel billions of years before reaching Earth. By studying the brightness of these supernovae in distant galaxies, astronomers gained a powerful new tool for measuring the scale of the universe. During the 1990s, two international research teams began using Type 1a supernovae to measure how the universe has expanded over time. One group was known as the Supernova Cosmology Project, led by physicist Saul Perlmutter. The other team was called the High Z Supernova Search Team, led by astronomers Brian Schmidt and Adam Riess. Both teams were searching for distant supernova explosions in galaxies billions of light-years away. Their goal was to answer a fundamental question about the universe. Ever since Edwin Hubble discovered in 1929 that galaxies are moving away from each other, astronomers had known that the universe is expanding. But the rate of that expansion was expected to change over time. Gravity from all the matter in the universe should gradually slow the expansion. Just as a ball thrown upward eventually slows as gravity pulls it back down, the cosmic expansion was expected to decelerate as galaxies pulled on each other through gravity. The key question was how fast that slowing was occurring. By measuring the brightness of distant Type 1a supernovae, astronomers could estimate their distances. By comparing those distances with the redshift of the galaxies hosting the supernovae, they could determine how fast the universe was expanding at different points in the past. When the teams began analysing their data, they encountered a surprising result. The distant supernovae appeared dimmer than expected. At first, researchers considered possible explanations such as dust, obscuring the light, or errors in measurement. But as more observations accumulated, the pattern became clear. The supernovae were farther away than predicted. This meant that the expansion of the universe was not slowing down. Instead, it was speeding up. The universe was expanding at an accelerating rate. This discovery was announced in the late 1990s and quickly became one of the most important breakthroughs in modern cosmology. Something in the universe was driving galaxies apart with increasing speed. Astronomers now refer to this mysterious phenomenon as dark energy. Dark energy appears to act as a kind of repulsive force built into the fabric of space itself. As space expands, dark energy causes the expansion to accelerate rather than slow down. The nature of dark energy remains one of the greatest unsolved problems in physics. Yet the discovery itself depended on a very specific kind of stellar explosion. Type 1a supernovae. And those explosions occur because of binary star systems. Without a white dwarf gathering mass from a companion star and eventually exceeding the Chandrasekhar limit, these thermonuclear explosions would not occur in the way they do. In an extraordinary sense, the quiet interaction between two stars in a distant binary system helped reveal one of the deepest mysteries of the universe, the expansion of space itself. The discovery earned Saul Perlmutter, Brian Schmidt, and Adam Riess the Nobel Prize in Physics in the year 2011. Their work demonstrated how the careful study of stellar explosions could reshape our understanding of the cosmos. From the outside, a Type 1a supernova appears as a brilliant flash of light in a distant galaxy. But behind that flash lies a long story. Two stars orbiting each other, one slowly transferring matter to the other, a white dwarf quietly growing heavier over millions of years, and finally a sudden release of energy so powerful that it becomes visible across billions of light years. A brief cosmic beacon, one that helped humanity discover that the universe itself is expanding faster with time. Some stellar remnants are so dense that even the strange physics of white dwarfs is not enough to support them. When a massive star reaches the end of its life and its core collapses under gravity, an entirely different kind of object can form. This object is known as a neutron star. A neutron star is the collapsed core of a once massive star that ended its life in a powerful supernova explosion. During that collapse, gravity compresses the core to such extraordinary densities that electrons and protons combine to form neutrons. The result is a sphere of matter unlike anything found under ordinary conditions. A typical neutron star contains about 1.5 times the mass of the Sun, yet its diameter is only about 20 kilometers. That is roughly the size of a small city. The density of such an object is almost impossible to imagine. A single teaspoon of neutron star material would weigh billions of tons under Earth gravity. In these extreme conditions, matter behaves in ways that challenge our understanding of physics. The idea that such objects might exist was first suggested during the 1930s. Physicist Lev Landau explored the possibility that gravitational collapse could compress matter beyond the density of ordinary atomic nuclei. Around the same time, astronomers Walter Baird and Fritz Zwicky proposed a bold idea while studying supernova explosions. They suggested that supernovae might represent the transformation of an ordinary star into a neutron star. At the time, this concept seemed almost unbelievable, but decades later, observations confirmed that neutron stars are very real. In 1967, the discovery of pulsars provided the first direct evidence. Pulsars are rapidly rotating neutron stars that emit beams of radio waves from their magnetic poles. As the star spins, these beams sweep across space like the light from a lighthouse. When one of these beams crosses Earth, radio telescopes detect a brief pulse of radiation. Some pulsars rotate dozens of times per second, producing extremely precise pulses that can be measured with remarkable accuracy. Neutron stars become even more fascinating when they appear in binary systems. Just like white dwarfs, neutron stars can have companion stars that transfer gas through Roche-Lobe overflow. When this happens, the neutron star begins pulling matter from its partner. The gas falling toward the neutron star forms an accretion disk, spiraling inward under the influence of gravity. But the gravitational field of a neutron star is far stronger than that of a white dwarf. Because the neutron star is so compact, matter falling toward it accelerates to incredible speeds. As the gas approaches the surface, its gravitational potential energy is converted into heat. Temperatures near the surface can reach tens of millions of degrees. At these temperatures, the gas emits powerful X-rays. Binary systems containing a neutron star and a mass-transferring companion are therefore known as X-ray binaries. They are among the brightest X-ray sources in the sky. Unlike visible light, X-rays cannot easily pass through Earth's atmosphere. This means astronomers must study these systems using space-based observatories designed specifically to detect high-energy radiation. One of the most important of these observatories is the Chandra X-ray Observatory, launched by the United States Space Agency NASA in the year 1999. Chandra carries highly sensitive instruments capable of detecting faint X-ray sources across vast distances. Its mirrors focus incoming X-rays onto detectors that record the energy and arrival time of each photon. Using Chandra and other space telescopes, astronomers have identified many X-ray binary systems throughout the Milky Way and in nearby galaxies. These observations reveal extraordinary physical environments. As gas falls onto the neutron star's surface, it can pile up in a thin layer. Under the intense gravity, this layer becomes compressed and heated until nuclear reactions ignite. In some cases, these reactions produce sudden flashes of X-rays known as X-ray bursts. These bursts occur when accumulated hydrogen and helium undergo explosive nuclear burning on the surface of the neutron star. The flash may last only a few seconds, but during that brief moment the system becomes dramatically brighter in X-rays. Such events allow astronomers to study nuclear physics under extreme conditions that cannot be reproduced in laboratories on Earth. Neutron stars also possess incredibly strong magnetic fields. Some neutron stars have magnetic fields trillions of times stronger than Earth's magnetic field. These fields guide the flow of incoming gas toward the magnetic poles of the star. As matter crashes onto the surface along these magnetic funnels, it releases bursts of radiation that can be detected across the galaxy. Because neutron stars rotate rapidly, these hotspots may sweep through space in repeating patterns, producing pulsations in the observed X-ray emission. Astronomers carefully study these variations to understand the structure of the neutron star and the behavior of matter in extreme gravitational fields. Neutron star binaries therefore provide a natural laboratory for studying physics at densities far beyond anything achievable on Earth. Inside a neutron star, matter is compressed to densities greater than those found inside atomic nuclei. Protons and electrons merge into neutrons, and the particles themselves may be packed so tightly that new forms of matter emerge. Some theoretical models suggest that the cores of neutron stars might contain exotic states of matter, such as hyperons or even quark matter, where the fundamental building blocks of protons and neutrons move freely. Observations of neutron star binaries help astronomers test these ideas. By measuring the masses, radii, and rotation rates of neutron stars, scientists can constrain the physical properties of ultra-dense matter. Every new observation adds another clue to the puzzle, and all of it begins with a simple gravitational partnership. Two stars orbiting each other. One star collapsing into an object so dense that a mountain of matter could fit inside a teaspoon. The other star slowly feeding gas into the immense gravitational well. Together they create a system where gravity, nuclear physics, and quantum mechanics meet under some of the most extreme conditions in the universe. Some stellar partnerships lead to environments even more extreme than those surrounding neutron stars. In certain binary systems, one of the stars has collapsed into the most mysterious object predicted by modern physics: a black hole. The existence of black holes arises naturally from the theory of general relativity, developed by Albert Einstein in the year 1915. General relativity describes gravity not as a force in the traditional sense, but as the curvature of space and time created by mass and energy. According to Einstein's equations, if enough mass becomes concentrated within a sufficiently small region, the curvature of space-time becomes so intense that nothing can escape its gravitational pull. Not light, not matter, not even radiation travelling at the speed of light. The boundary surrounding such an object is known as the event horizon. Once anything crosses this boundary, it cannot return. Black holes were originally considered mathematical curiosities. For many years, scientists debated whether they could exist in the real universe. Yet as astronomical observations improved during the 20th century, evidence began to accumulate that black holes might indeed be present among the stars. The term black hole itself was popularized by the physicist John Wheeler during the 1960s. Wheeler recognized that these objects represented a unique endpoint of gravitational collapse. If a massive star exhausted its nuclear fuel, and its core collapsed beyond the limits supported by neutron degeneracy pressure, gravity would continue compressing the matter inward. No known force could halt the collapse. The result would be a region where gravity becomes so strong that an event horizon forms, sealing the interior from the rest of the universe. But detecting black holes presents a challenge. Because black holes emit no light of their own, they cannot be seen directly through telescopes. Astronomers must instead look for the effects black holes have on their surroundings. Binary star systems provide one of the most powerful ways to identify them. In some cases, a massive star ends its life in a supernova explosion that leaves behind a black hole rather than a neutron star. If that star had a companion before the explosion, the companion may remain in orbit around the newly formed black hole. From Earth, astronomers may see only the visible companion star. However, if that star begins losing gas through Roche-Lobe overflow, the black hole can capture this material. The gas forms an accretion disk as it spirals inward, just as it would around a neutron star or white dwarf. But the gravitational field near a black hole is far stronger. Gas falling toward the event horizon accelerates to extraordinary speeds. As it compresses and collides within the accretion disk, temperatures rise to millions of degrees. At these temperatures, the disk emits intense X-rays. This radiation can travel across the galaxy and reach detectors aboard space-based observatories. One of the first strong candidates for a black hole binary system was discovered in the constellation Cygnus. The system is known as Cygnus X-1. Cygnus X-1 was first identified during the 1960s as a powerful X-ray source. Astronomers soon realized that the radiation originated from a binary system containing a visible blue supergiant star. Careful measurements of the star's motion revealed something remarkable. The visible star was orbiting an unseen companion with a mass several times greater than the Sun. Yet no ordinary star could be detected at that location. If the unseen object were a normal star, it would produce detectable light. If it were a neutron star, its mass would likely fall below about 3 solar masses. But the inferred mass of the invisible companion exceeded that limit. The most likely explanation was that the companion was a black hole. Cygnus X1 therefore became one of the earliest and most convincing pieces of observational evidence that stellar mass black holes exist in nature. Since then, astronomers have discovered many other black hole candidates in binary systems throughout the Milky Way and beyond. These systems provide a remarkable opportunity to study the physics of strong gravity. Among the scientists who have contributed greatly to our understanding of black holes is the physicist Kip Thorne. Thorne spent decades developing theoretical models describing how matter behaves near black holes and how black holes interact with their surroundings. His work helped explain how accretion disks around black holes can produce some of the most energetic phenomena in the universe. As gas spirals inward within the disk, enormous amounts of gravitational energy are released. In fact, accretion onto a black hole can convert a significant fraction of the falling mass into energy. This efficiency can be far greater than the energy produced by nuclear fusion inside stars. Some of this energy emerges as high-energy radiation, while some of it drives powerful outflows known as relativistic jets. Relativistic jets are narrow beams of charged particles launched outward from the regions near the black hole at speeds approaching the speed of light. These jets can extend for enormous distances, sometimes stretching for thousands of light years into surrounding space. Although the exact mechanism responsible for launching these jets remains an area of active research, magnetic fields appear to play a crucial role. Magnetic field lines anchored within the accretion disk can become twisted by the rotation of the disk and the black hole itself. This twisting can channel energy and particles outward along the rotation axis, producing highly focused jets. Even in smaller binary systems, these jets can be detected through radio telescopes. Some systems exhibit brief but powerful outbursts in which the jets suddenly brighten and expand. These events provide valuable information about the physics occurring near the event horizon. Black hole binaries therefore serve as laboratories for studying gravity under extreme conditions. By observing how gas moves within the accretion disk, how radiation emerges from the system, and how jets form and evolve, astronomers can test the predictions of general relativity in environments far more extreme than anything within our solar system. At the same time, these systems remind us how interconnected stellar evolution can be. A massive star is born within a molecular cloud. It shines brightly for millions of years before collapsing in a supernova explosion. Its companion star continues orbiting the remnant core, now transformed into a black hole. Gas begins flowing across the gravitational boundary between them, and suddenly the quiet binary partnership becomes one of the most energetic systems in the galaxy, a dark object that cannot be seen directly. Yet its presence revealed by the motion of a companion star, the glow of a blazing accretion disk, and the brilliant streams of particles racing outward at nearly the speed of light. Gravity does not only hold stars together. Under certain circumstances, it can also slowly drain energy from their motion in a subtle and almost invisible way. This idea comes from one of the most remarkable predictions of Albert Einstein's theory of general relativity. General relativity describes gravity not as a force pulling objects together, but as the curvature of space and time created by mass and energy. Massive objects bend the fabric of space-time around them, and other objects move along the curved paths created by that distortion. But Einstein's equations reveal something even more intriguing. When massive objects accelerate, they do not simply move through space-time. They can also create ripples within it. These ripples are known as gravitational waves. A gravitational wave is a traveling disturbance in the geometry of space-time itself. As the wave moves outward, it stretches space in one direction while compressing it in another. The distortion is incredibly small, but it carries energy away from the system that produced it. Einstein predicted the existence of gravitational waves in the year 1916. For decades afterward, however, they remained purely theoretical. The waves were expected to be extremely weak, making them extraordinarily difficult to detect. Yet certain cosmic systems should produce them continuously. Binary stars are among the most important examples. Whenever two massive objects orbit each other, they accelerate as they follow their curved paths around the shared center of gravity. According to general relativity, this accelerating motion generates gravitational waves that propagate outward through space. As the waves carry energy away, the binary system gradually loses orbital energy. This loss has a specific consequence. The stars slowly spiral toward each other. The orbit shrinks by a tiny amount over time, a process known as orbital decay. For most ordinary stars, this effect is extremely small. The stars are relatively far apart, and their masses are not large enough to produce strong gravitational radiation. But when the objects involved are extremely dense, such as neutron stars or black holes, the effect becomes much more noticeable. During the early 1960s, physicists Peter Peters and Jay Matthews developed mathematical formulas describing how gravitational waves remove energy from orbiting systems. Their calculations showed how the orbital separation between two objects gradually decreases as gravitational radiation carries energy away. The equations predicted that the rate of orbital decay depends on several factors, including the masses of the objects, the distance between them, and the shape of their orbit. Although the mathematics behind these formulas can be quite complex, the underlying idea is straightforward. As the stars orbit, they emit gravitational waves. Those waves carry energy outward into space, and because the system loses energy, the orbit slowly contracts. For many years, this prediction remained untested. Astronomers needed to observe a system where the effects of gravitational radiation would be large enough to measure. Such a system was discovered in the year 1974 by two radio astronomers, Russell Hulse and Joseph Taylor. They were using the Large Radio Telescope at the Arecibo Observatory in Puerto Rico to search for pulsars, rapidly rotating neutron stars that emit pulses of radio waves. During their observations, they discovered a pulsar that behaved in a particularly interesting way. The pulsar was not alone. It was orbiting another neutron star in a tight binary system. This system, now known as the Hulse-Taylor binary pulsar, consists of two neutron stars orbiting each other once every several hours. Because neutron stars are incredibly dense, the gravitational forces involved in the system are enormous. As the two stars orbit each other, they produce strong gravitational waves. Hulse and Taylor carefully monitored the timing of the pulsar's radio pulses over many years. Pulsars are extraordinarily precise cosmic clocks. Each rotation produces a radio pulse that arrives on Earth at regular intervals, often with precision better than a millionth of a second. By measuring tiny variations in the arrival time of these pulses, astronomers can determine the exact motion of the pulsar within its orbit. What Hulse and Taylor discovered was remarkable. The orbital period of the system was gradually shrinking. The two neutron stars were slowly spiraling closer together. The rate of orbital decay matched precisely the value predicted by the equations developed by Peter Peters and Jay Matthews for gravitational wave emission. This observation provided the first strong indirect evidence that gravitational waves truly exist. For their discovery, Russell Hulse and Joseph Taylor were awarded the Nobel Prize in Physics in the year 1993. Their work demonstrated that binary star systems can serve as natural laboratories for testing the predictions of general relativity. While astronomers were studying these systems in space, physicists on Earth were working to detect gravitational waves directly. One of the pioneers in this effort was Ronald Drever, a Scottish physicist who helped develop early designs for gravitational wave detectors. Drever and his colleagues proposed using laser interferometry to measure the incredibly small distortions caused by passing gravitational waves. The idea involves sending laser beams along long perpendicular arms and measuring tiny changes in the length of those arms as gravitational waves stretch and compress space. These changes are extraordinarily small, far smaller than the width of an atomic nucleus. Detecting them requires instruments of astonishing precision. Drever's work contributed to the development of large-scale interferometric detectors that would eventually lead to the construction of observatories such as the Laser Interferometer Gravitational Wave Observatory. These detectors were designed to capture the faint whispers of gravitational waves produced by some of the most violent events in the universe. But long before those detectors succeeded, binary star systems had already revealed the existence of gravitational radiation through their gradual orbital decay. Two neutron stars orbiting one another, each revolution sending ripples outward through the fabric of space-time. With every orbit, a tiny fraction of energy escapes as gravitational waves. Over millions of years, the stars draw closer and closer together, their orbits slowly tightening. their motion quietly sculpted by the gentle loss of energy carried away through the invisible vibrations of space-time itself. When two compact stellar remnants orbit each other closely enough, their long dance eventually reaches a dramatic ending. Over millions, or sometimes billions of years, gravitational waves slowly drain energy from the system. Each orbit becomes slightly smaller than the one before it. The stars spiral closer together, moving faster and faster as gravity pulls them inward. In the final moments, the motion becomes extraordinary. Two neutron stars or black holes may circle each other hundreds of times per second, their separation shrinking rapidly. The gravitational waves produced during this stage become far stronger than those emitted during the earlier parts of the orbit. Eventually, the two objects collide and merge. For many decades, scientists believed that such mergers must occur throughout the universe. Yet detecting them directly required technology capable of measuring incredibly small disturbances in space-time. That technological achievement arrived with the construction of large gravitational wave observatories on Earth. Two of the most important facilities are known as the Laser Interferometer Gravitational Wave Observatory and the Virgo Interferometer. The Laser Interferometer Gravitational Wave Observatory, commonly called LIGO, consists of two massive detectors located in the United States, one in the state of Washington and another in Louisiana. Each facility uses laser beams traveling along long vacuum tunnels, arranged in an L-shaped configuration. The Virgo Observatory operates in Italy and uses a similar design. Inside these detectors, laser beams travel back and forth along arms several kilometers long. Mirrors suspended with extraordinary precision reflect the light thousands of times. If a gravitational wave passes through the detector, the stretching and squeezing of space-time slightly changes the length of the arms. These changes are incredibly small, far smaller than the diameter of a proton. Yet with careful engineering and sophisticated analysis, the detectors can measure them. In the year 2015, the LIGO detectors recorded the first direct observation of gravitational waves. The signal came from the merger of two black holes located more than 1 billion light-years away. This discovery confirmed a major prediction of Einstein's theory of general relativity and opened an entirely new way of observing the universe. But an even more remarkable event occurred just 2 years later. In August of the year 2017, both LIGO detectors and the Virgo Observatory detected a new gravitational wave signal. The pattern of the signal revealed that it came from two neutron stars spiraling toward each other. The event was designated GW 170817. Unlike previous black hole mergers, this collision produced not only gravitational waves, but also a flash of electromagnetic radiation. Within seconds of the gravitational wave detection, space telescopes observed a burst of gamma rays arriving from the same region of the sky. Astronomers around the world quickly pointed their telescopes toward the source. Within hours, optical observatories identified a faint but rapidly brightening object in a distant galaxy, about 130 million light-years away. This object was the aftermath of the neutron-star merger. For the first time in history, scientists were able to observe the same cosmic event through both gravitational waves and traditional electromagnetic radiation. This marked the beginning of a new era known as multi-messenger astronomy. In multi-messenger astronomy, researchers combine different forms of information carried by different cosmic messengers. Light, gravitational waves, neutrinos, and cosmic rays all provide different insights into the same event. By studying them together, scientists can build a much more complete understanding of what occurred. The neutron-star merger of 2017 revealed another fascinating phenomenon. The collision produced a powerful explosion known as a kilonova. The concept of kilonova explosions had been predicted by astrophysicist Brian Metzger and his colleagues several years earlier. Metzger proposed that when neutron stars merge, some of their neutron-rich matter would be ejected into space at tremendous speeds. This matter contains enormous numbers of free neutrons. Under such extreme conditions, atomic nuclei can capture neutrons extremely rapidly in a process known as rapid neutron capture, or R-process nucleosynthesis. In this process, heavy atomic nuclei form by rapidly absorbing neutrons before they have time to decay. The result is the creation of some of the heaviest elements in the periodic table. Elements such as gold, platinum, and uranium are believed to form primarily through this process mechanism. The neutron-star merger observed in 2017 provided the first direct evidence that kilonova explosions truly occur. As the ejected material expanded into space, it produced a glow that gradually changed colour over several days. The changing colours matched theoretical predictions for the radioactive decay of heavy elements formed through R-process nucleosynthesis. In other words, the collision of two neutron stars had forged precious metals in space. Gold, platinum, and other heavy elements were literally being created in the aftermath of the merger. This realization connected one of the most violent events in the universe to something quite familiar on Earth. Many of the heavy elements found in our planet, including those used in jewelry and advanced technologies, were likely formed during similar neutron star mergers billions of years ago. The atoms that make up rings, coins, and electronic components may have originated in such distant cosmic collisions. The observation of GW 170817 therefore answered several long-standing questions at once. It confirmed that neutron star mergers produce gravitational waves detectable from Earth. It demonstrated that these events also emit electromagnetic radiation across many wavelengths, and it provided strong evidence that they create heavy elements through R-process nucleosynthesis. The discovery transformed the study of cosmic events. Instead of relying on a single type of signal, astronomers could now observe the universe through multiple channels simultaneously. Gravitational waves reveal how massive objects move and collide. Light reveals how matter behaves in the aftermath. Together they provide a far richer understanding of the cosmos. At the center of these discoveries lies the quiet evolution of binary star systems. Two neutron stars orbiting each other for millions of years, their orbit shrinking slowly as gravitational waves carry energy away, until one final moment when their long dance ends in a brilliant flash. A collision powerful enough to ripple the fabric of space-time and create the elements that would someday become part of planets, oceans, and even ourselves. If we could travel far beyond the Milky Way and look back at our galaxy across billions of years of time, we would see something remarkable. The galaxy does not remain chemically the same throughout its life. Instead, it slowly changes composition as generations of stars are born, live out their lives, and return material back into interstellar space. Astronomers call this long process galactic chemical evolution. The phrase may sound technical, but the idea is beautifully simple. The universe began with only the lightest elements. Hydrogen formed first, along with helium and tiny traces of lithium. These elements were created during the earliest moments of cosmic history, only minutes after the Big Bang. Everything heavier had to be built later. Stars became the factories where new elements were forged. Inside stellar cores, nuclear fusion gradually transforms lighter atoms into heavier ones. Hydrogen becomes helium. Helium can fuse into carbon and oxygen. In the most massive stars, nuclear reactions eventually produce elements as heavy as iron. Yet the story does not end there. For the elements created inside stars to influence the galaxy, they must somehow escape the star and mix with the surrounding gas. This is where stellar deaths and stellar partnerships play a crucial role. Astrophysicist Francesca Matteucci has spent decades studying how galaxies change their chemical composition over time. Her work focuses on modelling the processes that distribute elements through galaxies as successive generations of stars evolve. In these models, stars are not isolated actors. Instead, they form part of an ongoing cycle of cosmic recycling. When stars die, they return enriched material to the interstellar medium. That material later becomes part of new stars, planets, and perhaps even life itself. Binary star systems contribute to this process in several powerful ways. One of the most important contributions comes from Type 1a supernova explosions. When a white dwarf in a binary system grows too massive and explodes, it releases enormous amounts of newly formed elements into space. These explosions produce large quantities of iron and other elements belonging to what astronomers call the iron peak. The expanding debris from a supernova spreads outward at speeds of thousands of kilometers per second. Over time, this material mixes with the surrounding interstellar gas. Eventually, the enriched gas may collapse again to form new stars. When those stars form, they contain not only hydrogen and helium, but also the heavier elements produced by earlier generations. Astronomers refer to these heavier elements collectively as metals, even though many of them would not normally be considered metals in everyday chemistry. In astronomy, any element heavier than helium is called a metal. As galaxies age, the abundance of these elements gradually increases. but Type 1a supernovae are only part of the story. Another major source of heavy elements comes from the collisions of neutron stars in binary systems. As we explored earlier, when two neutron stars merge, they can eject neutron-rich material into space during a kilonova explosion. Within that expanding cloud of matter, rapid neutron capture reactions produce some of the heaviest elements in the periodic table. This process, known as R-process nucleosynthesis, creates elements such as gold, platinum, and uranium. These elements are incredibly rare compared with lighter elements like carbon or oxygen. Yet they are essential components of the chemical diversity we observe throughout the universe. Without neutron star mergers and similar extreme events, many of the heaviest elements might scarcely exist at all. The expanding debris from these mergers spreads through the surrounding galaxy, just as supernova debris does. Over time, it mixes with interstellar gas clouds that may later collapse to form new stars. When those stars form, they inherit the chemical fingerprints of earlier stellar generations. In this way, galaxies slowly evolve from simple compositions dominated by hydrogen and helium into richer mixtures containing dozens of elements. Planetary systems forming around younger stars therefore contain far more chemical diversity than the earlier stars did. Our own solar system formed about 4.5 billion years ago from a molecular cloud already enriched by many earlier generations of stars. The iron in Earth's core, the oxygen in our atmosphere, the calcium in our bones, and the gold in jewellery all originated inside stars or stellar explosions that occurred long before the Sun was born. Many of those events involved binary star systems, white dwarfs exploding as Type 1a supernovae, neutron stars merging in kilonova explosions, massive stars exchanging matter and evolving differently because of their stellar companions. Binary interactions can dramatically change the life paths of stars, altering when and how they release their material into space. Because of this, binary stars play a surprisingly large role in shaping the chemical evolution of entire galaxies. Their gravitational partnerships influence when supernovae occur, how heavy elements are produced, and how those elements spread through interstellar space. Francesca Mattiucci and other researchers studying galactic chemical evolution use detailed computer models to trace these processes over billions of years. By comparing model predictions with observations of real galaxies, astronomers can reconstruct how chemical enrichment unfolded across cosmic history. These studies reveal that stellar partnerships are not merely local phenomena affecting individual stars. They contribute to the long-term transformation of galaxies themselves. Across the Milky Way, countless binary systems quietly orbit each other. Some will remain stable for billions of years. Others will eventually erupt in spectacular explosions or merge in violent collisions. Each event adds new ingredients to the cosmic mixture. Atoms forged in stellar furnaces drift through interstellar clouds, eventually becoming part of new stars and planets. And somewhere, billions of years later, those atoms may become part of something even more remarkable, a living world. All of this begins with the quiet gravitational bond between two stars. A partnership formed in a collapsing cloud of gas, continuing through a long orbital dance and ultimately contributing to the chemical story of an entire galaxy.